My name is Milecia McGregor, and I'm a developer advocate at Iterative AI, where we work on quite a few open source tools for machine learning and data science projects. You can follow me on Twitter at Flipped Coding, or you can interact with the team directly on Twitter at DVC.org. So today I'm going to be talking to you about using reproducible experiments to create better models. So even before I started working at Iterative, I found DVC when I was working on like this crazy air guitar project where I was trying to process brain signals and make some kind of machine learning model out of that. So I'm super excited to talk to y'all about this today. So a couple of things, if you want to follow along, I do have a live demo and we'll see how that goes. You know, sometimes they work, sometimes they don't. But if you want to follow along, make sure you have Python 3 installed. Make sure you're using VS Code. You don't have to, it's just the IDE that I'll be doing the demo in. And you can find the project we'll be working with in this GitHub repo. So let's go ahead and just jump right on in. As you know, there are a few common issues that come up with any machine learning project you're working on, regardless of what stage you're in. So the main thing that we're trying to do is find the best combination of hyperparameters, algorithms, and data sets to get a model we feel comfortable deploying to production. So that means we'll probably end up doing some hyperparameter tuning. We'll probably go through a few different algorithms to check for things like performance, make sure our metrics look okay. And of course, we'll probably be working with different versions of our data sets. So maybe you start training with some gigantic CSV file, and then the next day you get another gigantic CSV file. So we have to keep track of all of these little things that go into the experiments we're running to make our models. And keeping track of all of those changes can be really challenging. Like I've seen people do all kinds of things to try to keep track of those changes. Some people try to use Git and GitHub to track everything, but then you run into the issue of having these super large files that just aren't compatible with Git. And there have been people that try to use spreadsheets with links to different Google Drives that have different data sets and code and configs associated with them. And if you're running hundreds of experiments a day, you can imagine how messy that's going to get really, really fast. So trying to keep track of all of those little changes you make for each experiment, it just gets super tedious and hard to manage. So over time, you're going to end up with thousands of experiments between multiple team members, and that just makes it hard to figure out which set of changes gave you the model you're currently looking at. So you might find this great model, like you give it the test data and you see that your metrics are just incredible. Maybe you have something like a ROC AUC value of like 97%. And of course, that's probably the model you're going to want to use in production. But now you're stuck at this point where you're like, wait a second, did I use this data set for this model? Was it this random forest classifier algorithm I used, or was it something else? Were these the hyperparameter values I used, or did I change this one before this model? And is this the same experiment that my coworker ran and they got different results? So over time, it's just really hard to keep track of all of those changes and follow which changes gave you the model that you're currently looking at. So let's talk about how to fix some of these common problems. This is kind of what it looks like when you're going through this experimentation phase, trying to find the best model that you can. So you might decide to update some parameters, but guess what? You probably need to bundle the data that you use for that particular training experiment. You'll probably need to have all of the hyperparameter values you used. And of course, you'll probably need, the script that you ran or the notebook that you used to get the metrics for the algorithm that you're training with. So you go through all of these different experiments and you end up with all of these different little bundles that tell you what exact changes and what exact data sets you were working with when you ran this particular experiment. So as you can see, you'll update some parameters, maybe you'll update the data set and some parameters, then just some more params, then you get more data and new params, and then you're adjusting params again. And you probably did all of that in 30 minutes or less. So you can imagine over the course of a day, how many of these little bundles that you will end up with. So let's just talk about a little background on hyperparameter tuning, which will take us into our live demo example shortly. So you're probably familiar with what hyperparameter tuning is. It is changing all of those little parameters that define your model. So these aren't the parameters that you get when you finish training. These are the parameters that actually make up your model. So for example, if you're doing a random forest classifier, you might have a max depth hyperparameter. And if you're working with neural nets or something, you might have the number of layers that you want for that particular experiment with the algorithm. So hyperparameter tuning produces a lot of different experiments. And I'm not sure about you, but I remember before I found some really good tools, trying to keep track of all of those little changes where, you might iterate through 100 different values for one specific parameter. That gets extremely tedious to keep track of. So we're going to look at a quick little example of how you might do grid search and random search for your hyperparameter tuning. So with grid search, we're more focused on checking every possible combination of hyperparameter values that we have. So you'll have a set of values for each hyperparameter, and as you run through experiments, you will go through every possible combination of those parameters. And with a random search, it's similar to a grid search in that you'll have this set of values associated to each hyperparameter, but you won't exhaustively go through all possible combinations. It will just skip around and try different value combinations, which is why it's random. But let's go ahead and take a look at this little demo I have. Let me see if I can switch to VS Code easily. Okay, it tells me that you all can see this, so I'm hoping that's true. But what we have set up here is a little project that uses DVC to track all of the experiments we run. So just a quick little background on DVC. It's an open source tool that lets you version your data sets so that you don't have to worry about how you're going to include them in your Git commits or how you'll reference them to the experiments you run. DVC just tracks those changes for you. So anytime you have an update to your data set, DVC is in the background, making sure that it basically keeps a record of those changes for your data set. So what we have here is a project that's already been initialized with DVC. And on top of the data version control, it also has this experiment functionality. So if you're familiar with something like MLflow, DVC is similar to that, except it is completely language agnostic. So you could use it with Python, R, Julia. If you're weird like me, JavaScript, you can use it in any project you want. You don't have to make any API calls to track your experiments. It's all here right in your repo. So this has DVC set up, and we'll take a really quick look at the YAML, because if you're familiar or learning about MLOps, we have a pipeline that will let us reproduce each experiment exactly as we ran it the first time. So we have a prepare stage where we go through and we get the data out. We have a featureize stage where we take that data and do some things to it. Then we get down to the train stage, which is one of the more important ones because it's how we get the model that we'll be testing with. And lastly, we have this evaluate stage. So this is where we have our model and we want to check our metrics and see how well this model does on our test data set. And then just to take a quick look at the train script that we'll be running, we have some image data that we'll be just trying to classify really quickly. And we're just using a random forest classifier here. So we have a few different hyperparameter values that we'll be doing some tuning on. And at the end of the script, we just print out our model as a pickle file. So now that you have some background on what's happening in this repo, let's take a look at our super robust grid search. It's not really that robust, but it's robust enough for what we need. And we've had quite a few people in the community take this script and modify it to match whatever their needs are. So basically what we have here are our two hyperparameter values. And before we dive in, there's one more file I need to show you. So part of the coolness with DVC is that it gives you this kind of granular control over how you run experiments. So I know there's some other tools out there that let you set up these MLOps pipelines, but they make you run through every stage, even if a certain stage hasn't had any updates. So with DVC, if we update the hyperparameters for our training stage, we won't have to go through and prepare the data again and featureize it because we haven't made any changes to that. So DVC is smart enough to notice when we've made any changes to different stages, when our data's been updated, when our code files have been updated. So in this case, we'll be mainly focusing on these hyperparameters in this train stage. So I'm going to go back to our grid search file, and you can see we have our NEST values, we have our min split values, and let's just do a quick update so that we have some fresh things to look at. So I'm not picking these values for any particular reason, just updating things so you get a better idea of like what this would look like in practice. So we have these arrays of values for each hyperparameter. And since this is a grid search, that means we're going to run an experiment for each possible combination of these values. So for the sake of time, maybe I'll get rid of that last one. But we're just going through using built-in Python subprocess and iter tools to run these different commands in our terminal with these different hyperparameter values. So if I go ahead and run this script, we should get all of these experiments being queued up by DVC. And what that means is we're going to be able to look at all of the potential experiments we have before we run them. And if you see some that might be duplicates of what your coworkers have run or duplicates of things that you've run before, you can go ahead and remove those. But since we have all those experiments queued up, let's take a look at this table. So as you can see, I ran some experiments a little bit earlier in a different branch. But if you look at all of these different hyperparameter values here, we do have every possible combination of these values. So that means when we go ahead and run the experiment, all of these hyperparameter values are going to have the metrics associated with them. So I'm going to go ahead and run these queued up experiments. So it might take just a couple of minutes since this is, it's a lot of experiments. But basically what's happening in the background is DVC is getting all of our data ready, and then it's going to go ahead and start running our train script here. So we'll give it a few minutes, and just in the normal live demo fashion, it's running slower than it did when I tried it earlier this morning. So yeah, I'll give it just a second and see what it comes up with. And let's see what we actually have in our table now. So I'm gonna put a few extra options on this just so we can see the exact data that we're looking at. So let's say params train dot. And we'll do the min split. Then let me get something else up. Let's see, what is the other? Let's just take a look at what we have. Oh, that's not what I wanted. So let me see, exp show. Let's just look at what the table has now. Okay, that feels like a live demo thing. I think I ran the wrong command, but that's okay. Let me get that right command really quick here. So if I do dvc-xp run -- run all, this should run all of those queued experiments. So that's why my terminal is gonna twitch about for a little bit, because it did have quite a few experiments to look through. And I'm not sure if I'll let it run all of them. It depends on how fast it feels like going, but it's feeling pretty fast right now. So hopefully nothing weird happens and it'll just get through all of them okay. Which it looks like it is. But I think there were, like, what is that? 16 experiments, maybe a few more, but definitely at least 16. So yeah, while this is running in the background, I do want to mention that there's just a lot of different ways that you can run experiments with DVC. So right now we have all of those queued up. And if you look in our params file, when it was queuing those experiments, these values were changing. So if you ever want to just manually update any parameters and run an individual experiment, you can come in the params.yaml and update the particular values that you want to see. And then the way that this works is we have a reference to these params. So in our DVC YAML, you can see where we have, like, down here, we have our train min split, NEST, etc. So I probably already ran one of these experiments, but let's look at the queued experiments we did get through. Aha, we have a lot of different metrics to look at now. So if you see here, we didn't individually update all of those hyperparameters. It just took our queued experiments and ran through this for us. And you can see all these different values and the associated metrics. So right now, if we're looking at our rock AUC value, it's looking like, actually, this one might be the best one. So we can come over here and see that's what the hyperparameter combinations were. It's a little bit large, but hey, it gave us the best rock AUC value. It looks like it gave us the best average precision. And now we know that based on all of these different experiments, which one we should probably run with. So I'm gonna go ahead and take this experiment ID here, and we'll clear out the terminal and do dvc-exp apply, and then paste that experiment in there, and voila, you have an exact reproduction of the best experiment from all of your experiments in your workspace. So that means our parameters are updated. That means our script is in the same state as it was when we ran this experiment. We have the same data. DVC just applied all of that from all of these different hyperparameters to our workspace. So now that we know what the best combination of hyperparameters are, we know that grid search told us some things, and we can move on to our random search, because who knows, maybe this will give us better values. So if we look at that table again and we see what that best combination was, so it's pretty far up there, but let's look at maybe what was second best. So that's looking like somewhere, this one is probably second best. So let me highlight this row so I know what I'm looking at. Whoop. So it's looking like a min split or a NEST value of 65 and 420. So now let's do our random search. Let's say we're gonna go from, I don't know, 250 to 3,500. Let's just be a little crazy here. And then with this one, we'll go from 500 to 7,000. Of course, you'd probably not do a range this large, but just for the sake of this example, we're going to go ahead and look at some crazy values. So this is a similar script to our grid search, with a few changes, of course. But since we don't have to loop over all of the possible hyperparameter values, thankfully, because this range is pretty large, we're going to just give each hyperparameter a range of values that we want to randomly pick from. And we're only going to run 5 experiments this time instead of 16. So I'm going to go ahead and run this script. And you'll see it's going to queue up 5 of those experiments for us. So now if I go to the table again, let me make this quite a bit bigger. You can see at the bottom, we do have some queued experiments. So let's find those new ones. So these are the queued experiments from that random search we just did. So let's go ahead and run that. So I'm going to leave the table and clear my terminal. We're going to do dvc exp run -- run all. And my terminal's going to do the little twitchy thing for a bit, and then it's going to run those queued experiments. Okay, there we go. It's running. It's always a little scary when it just stops for a second. So it's looping through those queued experiments. And then we're going to get to do something pretty cool. So once our random search is finished, we're going to take a look at some plots and compare experiments that way. Okay, it's going really fast. I like it when it does that. All right, so looks like we've run all of the queued experiments we can without running into duplicates, because of course I ran some stuff earlier and forgot to clear out my workspace, but it's fine. So let's take a look at our table again and see if we can find these new experiments, which of course are right here at the top. So these are those random hyperparameter values that were selected in our random search. And let's see how those metrics stack up. It looks like this one is probably as close as we got to our #1 experiment. So this will be a hyperparameter value of, yeah, we got an NEST of a little over 2,200. and we got a min split of a little over 6,700. Again, you probably wouldn't have hyperparameter values that large, but it's fine. So let's go ahead and compare some experiments. So I'm gonna look at this table one more time to figure out what are the best and the worst experiments. All of these are really good. Like to have a minimum rock AUC of 92, well, I'll take that. I'll take pretty much any of these models. But it looks like the lowest value is for this experiment down here. Or maybe that one. No, that one. So I'm going to take this experiment ID and I'm going to save it out somewhere else for just a second from now. And then it looks like the best value, yeah, I'll go with this one. So we'll take this experiment ID. And now I'm going to show you something cool we can do. So let me clear out the terminal. And we are going to look at a plot showing the difference between these experiments. So this will be DVC plots diff, and then we'll add in those experiment IDs. So let me grab the other one, paste that in there, and it creates this HTML file. So I'm gonna not open that in VS Code. Let me copy this. Actually, let me just drag this over to my browser. And then I'll share it with y'all in just 1 second. All right, so let me share this with you. So we ran all of those experiments and now we want to compare the plots between them. So we're comparing our precision and the recall between those two best and worst experiments, even though they were both really good. But you can see that DVC automatically generates this plot for you just based on the metrics you decide to output from your training script or from your evaluation script. So you can look at the TPR versus the FPR. Again, we got our precision and our recall, and you can see kind of which plot did better. So our best experiment was this, which number is this? The 27, yeah, the 27 one. That turned out to be our best experiment. But DVC just gives you a way to look at these plots really quickly. So if I go back to VS Code, oops, and I'm gonna clear out the terminal just because I like a clean terminal. But basically in this evaluate script we are just outputting some files from our metrics we use. So you can see where we dump the precision, the recall, and the threshold into this PRC JSON file. You can see here where we output the FPR and TPR into this rock file. And then you can see where we output our main metrics, our average precision and our rock AUC into this scores file. So these values aren't coming from DVC at all. DVC is just using the outputs it sees in these files to generate those plots I just showed you. So I just wanted to be super transparent with where everything is coming from and how things are being generated. So now you see it's nothing special to DVC. You would probably output these metrics anyways so that you can compare with your teammates and just look at how well your experiments are performing. DVC just makes it even easier to do that. So now that you've seen how this works with a live example that actually worked without problems, let's get back into the presentation. So I'm going to switch over here. And if you were curious, this is the command that we ran to generate those plots. And the reason that we're using a tool like DVC to handle all of these experiments, I'm not sure if you noticed how long that table was getting in the terminal, but when you run a lot of experiments really quickly, you can end up with hundreds, thousands of them. And DVC just gives you an easy way to have an organized view of everything. You see that you can quickly compare different experiments in our plots. You can even compare metrics directly with some other DVC commands to see like the change in your average precision and ROC AUC across these different experiments we've run. So hopefully this gave you a good idea about why we want to have reproducibility in our experiments as we're training and testing different models. And hopefully you also see how DVC simplifies this so that you don't have to do a git commit every time you change a hyperparameter. You don't have to make a new zip file to work with different data sets. You don't have to do a git commit and write this zip file for when you decide to update hyperparameters and change the algorithm that you're experimenting on. So I just have a few key takeaways that I hope you get from this talk today. The first is adding reproducibility to experiments is important. So you noticed how we had our best experiment with the highest ROC AUC value. Just imagine what it would be like if you had all those experiments and you couldn't quickly reproduce them, because we did at some point take our best experiment and apply the exact hyperparameters, data, and code we had to our current workspace. Think about doing that without a tool. That would probably mean searching through a bunch of git commits, trying to figure out which data set you were using, and maybe even then you won't have it quite the exact same. And again, I hope that you see DVC helps you track all of these different parts of your experiment. I know when I was working with my air guitar project, I had a bunch of different data files, and trying to track those manually was a pain. But once I started using DVC, it just made it honestly more fun to run experiments, because it took away that nagging thought in the back of my head of, oh man, I gotta make sure that I keep track of what data did I use here? Did I try this algorithm? And then you try taking notes to keep up with everything, and it doesn't work out long term, because you might run some experiments 2 weeks later, and then you're like, wait a second, I remember I did this before, and it's gone. So my last takeaway is to not be afraid to try new tools. So you might use MLflow, you might use something like Neptune AI or TensorBoard or any other type of tool to track your experiments and keep up with your data. Just don't be afraid to try new stuff. Like, I personally really like DVC, but I understand that some projects might do better with other tools. Just try them out. Don't try to make this yourself, because there are a lot of different teams working on these tools. It's not cheating if you don't write every piece of code for everything you do on a project. Just try the tools. And just a few resources. If you are interested in learning more about DVC, make sure you check out our docs website. And if you have any specific questions or you run into some weird errors that you aren't sure why they're happening, make sure you join our Discord, because you will have direct access to the engineering team and they're super responsive, and issues that you bring up, they could end up on the roadmap. It's happened quite a bit before. So feel free to reach out to us and ask any questions you have. And if you're looking for something to like share those plots with your teammates, like I showed you earlier, check out Iterative Studio. So it's just a way for you to share your experiments for any GitHub or GitLab repo you have, and everybody on the team can see the plots, the metrics, the branches. You can run experiments directly in there without pulling down the code. It just does a lot of cool stuff for you. And if you're interested in looking at these slides, you can find them on SpeakerDeck at this link. There's a few commands in here that'll show you how to look at the tables, how to run the experiments, plots. It's a lot of good stuff. But that is all I have for you today. So if you have any questions, please feel free to drop them in the chat.